comment that I ended with yesterday, but I want to start with today, was that the chi-square analysis tells us whether the outcomes are unusual, whether the outcomes are different from what we expected, assuming the H0 claim. Now, in section 11.1, the H0 claim was we had this particular model that we were judging against. In 11.2, we have the H0 claim that the two categorical variables that we're looking at don't affect each other. They're independent of each other. Now, the chi-square value, and then from that chi-square value, the p-value tell us whether we're unusual or not unusual. But it doesn't tell us how we are unusual. It doesn't tell us what things stand out about the outcomes. Okay? And the best way, as I finished off yesterday, the best way to determine what's unusual is to look at the contributors to the chi-square value. In the example that we finished off yesterday, we had the Italian wines and the French wines. Thank you, sir. They're all in there. Okay, we had the Italian wine and the French wine, and we had the Italian music and the French music and the no music and the other wine, and we're like, does the music playing affect the wine sales? And we got a chi-square value that was pretty large, 18. And they got a p-value of 0.001. So we said, oh yeah, that's a significant result. But the chi-square value in itself doesn't tell us which things had the most effect. What did we think we saw? We think we saw suppressed Italian wine purchases when French music was played, and enhanced Italian wine purchases when Italian music was played, and that shows up in the contributor values. We saw large chi-square contributors here and here. What was that again? That's when French music was played, we had extremely low Italian wine purchases. When Italian music was played, we saw enhanced Italian wine purchases, and it shows up through those contributor values. So chi-square tells you there is an effect. The contributors, or looking at this graphically, can give you insight on what effect was happening. Remember when Kyle looked at those three graphs and said, look, the Italian looks really small there. The Italian wine purchases look really small. Okay? That's the kind of insight. Okay? Top line, you're just looking at something's going on. Delve into the data, you delve into the graphics, you delve into the contributors, you find out what actually is going on. All right? And that's the follow-up analysis. Okay? In fact, those two areas that we pointed out contribute 77% of the overall chi-square value. Most of what's going strangely is going on in those two categories. So we talk about that. Italian wine purchases down with French music played. Sell more Italian wine when Italian music is played. All right. So let's continue on. I want to recall that we've done most of the ideas here before. Okay, all we're doing is expanding the kinds of problems we can solve, and we're saving ourselves time by looking at chi-square as compared to the individual tests of proportion. We could just as well, from chapter 10, compare P1 versus P2. Between two different populations, do we get different outcomes? The alternative hypothesis is P1 not equal to P2. Chi-square basically says, let's test all those proportions down a line. Does P1 equal P2 equal P3 equal P4? In other words, can we check whether any differences amongst these populations on these ideas? Now, if they were all the same, we might use the term that they were homogeneous. Is that an expression that reminds you of something from another class? From what? Biology. From biology? Homozygous? Is that the expression that gets used in biology? Or is it homogeneous? Okay. Meaning all the same. Okay. Well, if we're testing a H-dot claim that P1 is equal to P2 is equal to P3 is equal to P4 for every single subgroup in our population, we could be saying that we're checking not for independence, but rather for homogeneity. Is everything the same? Okay? Now, the chi-square value will be big enough. The p-value will be small enough if any one of those proportions ends up being different. Which is nice. I don't have to say, well, let's say I have 4 different subgroups in my population. Let's say we're talking about this school, and I've got freshmen, I got sophomores, I got juniors, I got seniors, and I've got staff people, like me. I got 5 different groups. If I wanted to test them pairwise, I could test freshman versus sophomore. And then I could test freshman versus junior, then freshman versus senior, then freshman versus staff. Okay, there's 5 tests I'd have to do to check for differences. Oh, but then I have to do sophomore versus junior, sophomore versus senior, and sophomore versus staff. There's 4 more. Sorry, 4 in the first one, 3 in the second group. So now I'm up to 7, 2 prop Z tests doing. Oh, then I got to do juniors versus senior, juniors versus staff. There's 2 more. Now I'm up to 9. And now I got to do seniors versus staff. I have to do 10 separate tests where I can do a single one test. I can do the single chi-square test for homogeneity. And our null hypothesis in that case would be all those proportions are the same. And our alternate hypothesis would be at least one of the proportions is different. All right.
I say at least 2.
Sorry, at least one is different. At least one is different than the other. So I guess at least 2 different. At least two of the proportions are not the same. Some of the proportions are not equal. That's a good way to think of it. Okay. And again, all we're doing is a chi-square and checking all those simultaneously. Okay. So here's our example. Now, in this particular example, we're testing treatments for drug addicts. We'd like to help them get off of their addiction. I think in this case it's cocaine users. So we've got a bunch of cocaine users that all want to not be addicted to cocaine. So we're going to do an experiment. We have a new treatment. I'm really bad at drug names. I think this is disaspramine. At least that's a good enough guess as far as I'm concerned. So here's our new treatment. And we want to know, does it do better than known treatments? Like lithium. Does lithium actually have an effect? Does lithium do better than just giving someone a placebo? So here's what we have. We've got a total of 24 people who are going to be given disaspramine. And after how much time? After 3 years, of the 24, 10 of them relapse, meaning they go back to using, where 14 stay clean. Hey, I've got 24 people who were given lithium, and of them, 18 relapse, and 6 of them stay clean. And I've got 24 people who were given placebo, 20 of them relapse, and 4 of them stay clean. And the question is, do we have convincing evidence that these treatments, the treatment choice makes a difference? If you look at it graphically, it looks like the proportion of desaspermine users it looks like it has a lower rate of relapse. But as we've seen before, does lower rate mean it's significant? Can't tell. Can't tell without running the statistics. All right? So let's go ahead and do the chi-square analysis for this. Now, if we're doing it under the focus of homogeneity, we're basically saying, do we think the proportion of people who relapse after using desaspermine, do we think it's equal to the proportion of people who relapse after using lithium as their drug to help them out of their addiction versus the proportion of people who relapse using placebo? There's our null hypothesis. All those proportions, the same. What's our alternate hypothesis? At least one of them is different. And the chi-square will give us a significant result if any one of them is different than the other two. All right. So let's go through this. I'd like you to get your calculator out. I just want to make sure one more time that you know how to get the data into your calculator and be able to and get the results out. All right. Let me switch over to my calculator. Oh, which one did switch? There we go. All right. So the test for homogeneity, like the test for independence, is going to be found we're going to get the data in under the matrix. So second matrix is above the reciprocal button, and we get that screen. Now, unlike the list button, we have to go over into edit mode. So we have to shimmy over to edit and then hit enter, and that will give us the space to enter our data.
Got it.
Okay? Now, what size matrix do we have? 3-2. Row column. Radio controlled. So 3-2. All right? And then let's go ahead and let's type in the numbers. 10. Enter. 14. Enter. 18. Enter. 6. Oops, not 16. 6. 20. And then 4. Great. So we got the matrix filled out. Now what?
Now you go to stat.
Stat. I'm going to go big screen too while I'm at it.
You go to test.
Okay. Go to stat, test.
And then go down. You keep on going down.
I actually like coming up from the bottom.
Go up and then go to C.
Go to C. Okay. Remember, chi-square test is the chi-square tested for independence and test for homogeneity, whereas the chi-square GOF is the goodness of fit test, in which we're comparing our data to some model, like in the M&M problem. All right, so chi-square test. Okay. Wait, I didn't put my expected data into B. It'll do it for you because it's an easy process for it. It'll do it for me. There we go. Too easy. And so for a lot of the easy part of the four-step process, what do we got? What do I expect you to write down?
The X squared value, P value, and
Okay, the chi-square value of 10.5, I expect you to write that down. I expect you to write down the degrees of freedom, which is 2, because we have 3 rows, 3 minus 1 is 2, and I have 2 columns, 2 minus 1 is 1, so 2 times 1, 2 degrees of freedom. And then you have to write down the probability statement correctly. Probability that chi-square is greater than 10.5 is equal to 0.005. Does that chi-square value, does that p-value alone prove that desaspermine is a better treatment than lithium?
No.
Thank you. The answer is no. It shows that there's a difference, but then it's up to us to say, where is the difference? From the graph, we saw that the desaspermine relapse proportion was smaller than the other two groups. I believe that's where the significance is. All right? See, you notice how subtle that language is? It says that there is a difference. It doesn't tell you where the difference is. You have to delve back into the data to figure that out. So there's your step 3 in the process. Let's go ahead and just use the mantra for step 4. Because the p-value is below 0.05, we reject H0. What was our H0 claim again? That all those proportions were the same. Now, if you want to use the words of independence, that's fine as well. In the independence version of this, it says that our H0 claim was that treatment choice and relapse are independent, meaning they don't affect each other. Our HA claim in the independence version of this is that they're not independent, that treatment choice has an effect on relapse. Either way is fine, but if we're using the words of homogeneity, we're using all those proportions were the same versus at least one of those proportions is different than the others. All right, so let's just finish it up. Because the p-value is so small, we reject H0. Our context statement. We believe that treatment choice has an effect on relapse. We believe that at least one of the proportions of relapse is different than the others. Either one of those statements works for me. It tells you what our conclusion is without going too far. Only after you say that, then you can say, I see the desaspermine I spit all over the place. The desaspermine numbers are much smaller than the lithium or the placebo numbers. I think desaspermine is a better treatment choice. Chi-square doesn't tell you that. The graphic tells you that. Or looking at the actual proportions tell you that. All right. I hope you see the point I'm making about the limitations of what chi-square tells you and what it doesn't tell you. All right. Let's continue on. I seem to have lost my controls there. All right. So, just to summarize what we've already said, if we're doing this as a test of homogeneity, the H0 claim is all three of those proportions. The proportions of relapse within those three treatment groups are the same. Our HA claim is that at least two of them are different. Is it P1 different than P2? Is P1 different than P1? One of those are different. Is P2 different than P3? One of those, there's a pair that are different. Okay. Oh, by the way, since it's a medical study, oh, they threw a little change at us. Do we have significance at the 0.01 level on our data? What did our calculator say the p-value was? 0.001? 005? So we're good, even at that level. All right, let's see if there's anything else that we want to point out. Oh, did we check? We didn't check our conditions. We didn't do our step 2. Do we have an unbiased sample? Answer? Only if they assign those, was it 3 times 24, 72 people to their treatment groups randomly. Do we meet the qualifications for unbiased? Okay. So, were the subjects assigned to the treatment groups randomly? The answer is yes. We get the unbiased. If they've not, then we've got to proceed with caution. Do we have a large sample size? We forgot to check that too. How do we check to see if we have a large enough sample size?
What's the every expected is what?
We've got to make sure that every expected value or every value in the expected matrix is bigger than 5. Let's double check that. Where do I go? Second matrix. Did I miss the button? Yep. And then we want to go B. And you'll notice that B, when we started this process, B was empty. Now B is a 3 by 2 matrix. Why? Because the chi-square test analysis made it a 3 by 2 matrix.
Do we have to empty it before going through?
Nope, it'll overwrite it. Okay. Every value in the expected matrix was bigger than 5. So we passed the large sample condition. Okay. Okay, now our calculator did it for us. Can we just review really quickly how it did that calculation? How did it get that expected number was going to be 16 for that cell? And the answer was it took the row total of 24, the column total of 30 plus that is 48, and the table total was 72. So it took and said 24 times 48 divided by 72, and that ends up being 16, or the expected number of relapses amongst the disaspermine treatment group, assuming all those proportions were equal, or assuming that treatment had no effect on relapse. All right. Now, again, most people in the course of doing real statistics don't ever calculate it by hand, but you know how those tests are written, and you know that they may throw a question like that at you at some point. All right. So all the expected counts are greater than 5, so our condition is met. Last question is, do we have independence? Meaning, is the population that we're working with bigger than at least 10 times our sample size? Do we think there are at least 720 cocaine addicts that would like to become clean? No. In the whole world? No. I think so. I'm going to guess so. Well, remember, to be in this treatment, the 70 people all had to say, yes, I'm an addict, and I would like to be not using anymore. Right? Well, that's why there are support groups like Narcotics Anonymous, or other treatment groups for like alcoholics and their addictions. Okay, so finishing up. Yep, we did that too. We got a chi-square value of 10.5. The probability of having that extreme high of a chi-square value by pure chance alone was 0.005, and because that's less than 0.01, we reject H naught. We believe there's significant evidence that at least one of those proportions is different. There's significant evidence that treatment choice does matter. Now the matter is which way do we go? All right. Okay. Your turn. Another one. Considering how easy it actually is to enter the data and get the numbers out, would you do that for me right now? Okay. So what do we have going on here? We're following 8,474 people with normal blood pressure all the individuals were free of heart disease at the beginning of the study. And then we also measured them on an anger scale, which measures how prone a person is to sudden anger. Researchers then recorded whether each individual eventually developed coronary heart disease. And here's the summary. So what's the question that we're asking here? Is there a relationship between being quick to anger and developing heart disease? And if so, what is that relationship? So what's the size of your matrix in this case? No, not 3 by 3. You gotta watch out for the thing that says total. So how many rows? 2. Oh, hey, get back. There we go. 2 rows. Or two categories of whether you get heart disease or whether you don't get heart disease. How many columns? 3. So rows, columns. So it's 2 by 3, and this is going to have 2 degrees of freedom, I believe. Okay. What do you got? All right. Yeah, you should be getting this in your calculator right now. Okay, I hear just someone say 3 by 4, and the answer is no. Watch out. There's a trap. I see what you're doing. You're trying to find out whether I'm quick to anger, and so I can get heart disease. This is all plots.
So it's a 4 by 3.
No.
It's 4 by 3. I'm 3 by 4.
Okay.
Oh,
Okay, let's look at it one more time.
1 by 2.
And then freeze the screen. All right. Now, are you just yanking my chain here, or do you really have an idea, a problem with how big this matrix is? We don't count the totals in either direction. They're there, but they don't become part of our matrix. The only thing that's in our matrix is the stuff in the center, which has 3 columns and 2 rows, or it's a 2 by 3 matrix. And when you get into your calculator, it should look like that. All right? Let's do the quick chi-square part of this. That should be easy. Stats, alpha C, whoops, test, alpha C, calculate. So what's our quick analysis of this? Chi-square is 16, p-value is 3.
It's small.
It's what?
I got 113 for the chi smaller than 3.
Did anybody else get 16.07 for their chi-square value? Oh, Danny.
You got that. Daniel doesn't know what he's doing.
He also thought there was 4 rows and 3 columns.
Okay. Did you put it in as a 2 by 3? Okay. Just double check your numbers. All right. So So I made a classic mistake interpreting the p-value. The p-value isn't 3, which makes no sense for a p-value because
Smaller
smaller
than B.
than
It's smaller than 0.
smaller than 0.
No.
Smaller than 0?
Smaller than 1.
Smaller than, yeah, smaller than 1. Okay, so the p-value is what? 0.0003? Pretty small. So there seems to be a relationship here. Now the question is, what relationship? It seems to be in a relationship. There seems to be a relationship between getting heart disease and being angry. Question is, what is the relationship? If I get more angry, does that get my blood going really fast and clears out all my arteries and makes me healthier? Or, and by suppressing my anger, by not letting myself angry, do I end up doing my heart damage? Or is it the other way around? By getting angry, I end up getting high blood pressure, which causes damage to my heart. The chi-square value doesn't tell you which way the relationship is. It just tells you that there is a relationship. So, let's find out what the relationship is. Okay, so what they do is they calculated amongst the low anger, the incidence of heart disease was 1.7% versus no heart disease was 98%. Amongst the moderate anger, the heart disease went up to 2.3, and amongst the high anger, the heart disease rate went up to 4.3. Now, let me get this straight. What kind of distribution did they use to try to make the case that the difference we are seeing is that if you get angrier, you increase your chance of heart disease? What kind of distribution is this where they only looked at these values to get those results? I'm sorry? I heard someone say skew left, and again, I think you're yanking my chain. It's a conditional distribution. So we can look at conditional distributions in order to figure out where the relationship is. We know there's a relationship because the chi-square value is high and the p-value is low. It looks like the angrier you get, the higher your chance of heart disease. Now, what it doesn't tell you, by the way, it doesn't tell you whether anger makes your heart weaker, or that because you have heart disease, maybe you're just angrier. It doesn't tell you which way how that relationship works, which is the cause and which is the effect. It just says that there's a relationship. So let's say I'm a health screener. Maybe I work for a insurance company like HAP or Blue Cross. Maybe I'm trying to set rates. Maybe I somehow find out that you're an angry person. Maybe I set your insurance rates a little higher because we think that you have a propensity, you have a higher chance of having heart disease. So that's an expensive proposition. My mom had open heart surgery this past December. She spent 21 days in a hospital. You know how expensive that is? 21 days in the hospital is more than I make in 3 years. Now, here's where it gets scary for me. Ready? How many people go on Facebook? How many people post things? How many people post angry things?
TPS truth.
That's Twitter. Okay, but can you imagine, armed with this knowledge that is somewhat public, insurance companies start hiking your rates. I have a former student, one of my Ferndale students from CASA. He can't post something without profanity. He can't. He's got like Facebook Tourette's. It's just like, it just spews out of him. I'm like, this kid's angry. He was really nice in my class, but it's like, boy, you're angry.
Freedom of expression.
And maybe that's the case, but can you imagine someone trolling that information and say, you know what? I think I would charge you a little bit more for your health insurance.
Or not hire you.
What's that?
I said or not hire you.
Or not hire you. That's probably the bigger problem that he. But of course, maybe he'll delete his Facebook account before he starts interviewing for
That's
that.
why I don't have a Facebook.
What's that?
I can look
They
at it
like use
before they
Facebook
hire
for
me.
colleges.
Yeah, he already got into U of M, so.
Obviously, you have
Well, no, I didn't see this vitriol until after he got into U of M, so. Okay. So anyway, I'm just throwing that out because using statistics, we can find out all sorts of things about you, and then make predictions about you. For example, I don't know if you heard, there was a news story. Target, the department store, monitors what you purchase, especially if you use a credit card. Every time you use that same credit card, they attach it to some custom ID, and they keep track of what you're purchasing. They recently said that they figured out that a girl was pregnant before she, a teenage girl, before she ended up telling her parents. Through the purchases that she made, they could figure out she was pregnant. Now, for Target, that's really important because if they can track you and they can hook you into buying things at Target while you're pregnant, you're likely to continue buying things at Target after you have the kid. And kids are expensive.
Target's so cheap.
What's that?
Target's like a cheap place to shop.
Well, well, I mean, they sell themselves as they have good deals and sure, but if you can if Target can convince you to buy your diapers there as compared to buying it at Sam's Club or Costco, Target's going to make a lot of money. If they can figure out a way to hook you in as a customer while you're about to have a child, they're likely to make a lot of profit off of you in the long term.
Target has everything.
Sam's Club's better.
No, Sam's Club is Walmart. Don't buy it. Don't shop it.
Same one as Walmart.
Okay. Anyway, Costco's where it's at.
Sam's Club.
Okay. All right. Continuing on. So, finishing off the idea. Chi-square value tells us that there's something going on. The no p-value says it's significant. The graph, using the conditional probabilities, tells you in what direction that relationship is. In this case, low anger, less heart disease, high anger, more heart disease. A relationship, not necessarily a causal relationship. All right. So, we've talked about looking at this from the standpoint of homogeneity, and we've talked about using the chi-square test from the standpoint of association or independence. If we say there is independence between two categorical variables, we say they don't affect each other. If we say there's no independence, it's like also saying that there is an association. There is some sort of effect between the two. All right. So just giving you all the different variations of the way that we could make our H0 claim and our HA claim. Difference of proportions. There is independence as an as an H0 claim. There's no independence as an HA claim. There's no association as an H0 claim. There is association as an HA claim. So all of those are different ways to look at those things in step one of our four-step process. All right. And of course, we still have to check our conditions. Large sample size, independence, and random. So I call test for independence, the test for homogeneity, the test for association. Essentially, I call them all just one big test. We call it the chi-square test. At least that's what they call it on your calculator. All right. Anything new here? No, the only thing new here is, again, the variations on our H0 and HA claim. Either if we're going to use independence, they are independent for H0, they're not independent for HA. If we're going to use association, There is no association H0. There is an association for HN. And then the rest of it is all the same. And continue on. Okay. What's going on here? Oh, this is just them calculating the chi-square value that we did pretty easily. Because all we did was we put the 2x3 matrix in there. The expected matrix was calculated for us. We didn't check our matrix to make sure that all the expected meets our condition, but it looks like they do. Our sample sizes are huge. Okay, and the only other question we didn't ask is, did we get the sample randomly? So is there a lack of bias? They say it is a random sample. And on the independence, I'm simply going to ask, do we think that there's at least 84,000 people out there that we could be checking for heart disease and anger? I'm like, yeah. All right. All the things are satisfied. 16.7. P-value of 0.00. 0.0003 as calculated by our calculator. Can I just do one more thing? And that is, we haven't dealt with that last question, and that is, what if, because we've got test writers that are really, really clever, what if we don't allow you to use the calculator to find the p-value? Can we do the same thing here? How many degrees of freedom? There are 84,000 people in the sample, so there's like 84,000 degrees of freedom? No, that's right. I led you into a trap again. How many degrees of freedom? 3 minus 1 is 2. 2 minus 1 is 1. 2 degrees of freedom. So we look at 2 degrees of freedom, and then what are we looking for our chi-square value? It was like 10.5? Okay, so I go in this column, I'm looking for 10.5. I see that 10.5 would have fallen in that area, and then we go upward to say, oh, that means our p-value is between 0.01 and 0.005. That's consistent with what we found on the calculator, just saying that I know that the test writers can write a question that will force you to use the table. So don't forget to learn how to use the table. Test writers can write a problem that will force you to have to do the calculation of degrees of freedom. So don't forget how to calculate the degrees of freedom. All right. I think we're almost done now. All right, because the p-value is less than 0.05, we reject H0. Higher blood pressure and heart disease seem to be related to anger. All right. Okay, let's just sum this up by saying, watch out again. Remember that the chi-square test, as I said before, it tells you that there is a difference. It doesn't tell you where the difference is. You got to delve deeper to find out what those things are. Remember that the chi-square tests are used for things where we're doing relationships between categorical variables. So please make sure that you're working with categorical variables. Remember the observed matrix is a set of counts. Should only be whole values in that matrix. Okay, if the data comes from 2 or more independent samples or treatment groups, then they say that what we're really looking for is homogeneity. If the data comes from a single sample with individuals classified according to categorical variables, then the chi-square test is really a test for independence or association. Again, and what effect does that have on you? It has the effect on how you write your H-0 claim. I believe that's it. Yep, there's our summary page, and you don't want me to go through the summary. I think I've summarized again and again and again. I think you're done listening to me. All right, I promised you time for work on your homework. You have time now to work on your homework. It's only about 10 minutes, but it's better than nothing. All right.